Hello, my name is Dan Low. In this video, I'm going to show you a language that is undecidable. So you can, using this formula, P equal to the set of the empty language. So what does that really mean? You're talking about the language undecidable. Okay. So when we say undecidable, or the first thing come to my mind is the Shakespeare, to be or not to be. That is the question or problem. So when you're talking about a question or problem, it's undecidable. It makes sense. But when you're talking about a language that is undecidable, so what does that really mean? Okay, so the language uh, is a set of strings. Okay, so this set of strings has nothing to do with the decidable or undecidable. So there got to be a connection between a language and a problem, right? Or a question. So the connection between a problem and a language, I'll give you an example. Like, let's say I have a problem Q. So the problem is basically, given three real numbers, A, B, and C. And the question is asking, does the quadratic equation ax squared plus bx plus c equal to 0 have a real solution? This is real, doesn't mean real or fake. It's a real number solution, okay? So everybody comes through elementary school will know the answer. The answer is yes, because you have quadratic formula. You can compute that, okay? So basically, there's an algorithm to do it. So this is decidable. And now the corresponding language to that problem Q is something like this. I use LQ as the language corresponding to this problem. Okay, and this language is a set of strings, and this string, I actually decompose into three components: A, B, and C. You can concatenate, okay, combine them together into a string. That's fine. But anyway, A, B, C are the three real numbers. Okay, you can convert the three real numbers into a binary representation. Using IEEE 7754 standard for the floating point representation. And then you can get a binary string. Okay, so this is a string for sure. And that will be the set of these strings, and each string represent the one instance of ABC, or one instance of the problem. And that is the coefficient of the quadratic equation, ax squared plus bx plus c equal to 0. And as long as those ABCs, okay, that causes this quadratic equation to have a real solution, okay, and then this ABC string will be included in the LQ. So LQ is for sure is a set of strings, such that this quadratic equation has a real solution. So that's the language according to the problem. Okay, so when we say Q, this problem is decidable, that is equivalent to say LQ, this language, is also decidable. Okay, if the language LQ is decidable, that means that we can find a tuning machine M that decides if a given string, okay, ABC, is in LQ. So this is called the membership test. To test a given string is in this language. Okay, so if we can find such a TM, okay, then Q is decidable. Okay, and that also equivalent to say that there is an algorithm, and the quadratic equation formula, that's an algorithm, and that will run on the input ABC, and the outputs yes or no, not somewhere in between. It had to be determinate. Okay, either yes or no. Okay, and then the Q is decidable. Also LQ is decidable. Okay, so now we make a connection between problem and language. Okay, so what's next? Next, we're gonna study a little bit about a set of languages. So we know the language is a set of strings. Okay, so In a language accepted by a TM, we call it the recursively enumerable or RE. So a language accepted by TM is called RE. Okay, and a set of languages is basically a set of sets of strings because each language is a set of strings. So now you have a set of sets of strings. Okay, so a language may have the infinite strings. For example, 0 and 1 n is actually n could be or 0, 1, 2, 3 all the way up to infinity. So this is infinity. So this language contains infinity number of strings. So the input to the tuning machine had to be finite. So it's not possible to ask a tuning machine to recognize a language because this language contains infinite number of strings. So we cannot represent the finite strings for the language. We cannot do that. So that it's not possible to do it that way. Okay. So instead, we could recognize the TM, or the tuning machine that accepts a language. So for example, this language is accepted by a TM. Okay. So we create another TM tuning machine to recognize this TM. Simply because the TM is finite. Okay. TM, the tuning machine itself is finite. Okay. So you can have a finite encoding, for a TM. Okay. And then we can recognize that TM as a string. Okay. So that's a sort of meta or string. Okay, you can call it meta string, a string that describes strings. Okay. So a property of the RE language. Okay, the property of RE language. RE language is the language that accepted by a TM called RE language. So a property of that is a set of RE languages. A set of RE languages we call a property. Okay. So we can let P be the set of RE languages that are context free. So in other words, this property P is basically the set of all the context free languages. Okay, so be the set of RE and context free languages is RE. Okay, so that is the P. But when we want to say P is decidable, undecidable. Okay, we can just using the original P as a set of language because as I say that the TM cannot recognize the languages themselves. Okay, but we can recognize the DM TM that represent those languages. So the LP is the language. Okay, for this property that contains all the tuning machines M. Those tuning machines is context free. That tuning accepts language. Okay, LM is L sub M is the language accepted by the tuning machine M. It's context free. So if you collect those tuning machines together, the tuning machine here we say tuning machine simply mean that this is the encoding or binary encoding for the tuning machine. Okay, so binary encoding is a string, is a binary string, by the way. So this LP is a set of those encoding, those binary strings for those tuning machines, and those tuning machines accept language or that are context free. So basically, LP is this. So we say P is decidable, undecidable. Simply you want to check if LP is decidable, undecidable. Okay. So unfortunately, LP is undecidable for this case. So context free, language, the property LP is undecidable. It's also equivalent to say P is undecidable. Okay, I don't prove here, but if you're interested, you can leave the message. We'll talk about that in the future. So now let's get on to what is the P equal to the set of the empty language. So empty. So P is not empty. Okay, P is not empty. By the way, P is a set of the empty language. So what does that really mean? So remember, P is a set of RE languages that are empty because this is a language, empty language. So P is the set of RE languages that are empty. So what's that language? So that language basically is the collection of all the tuning machines, such that the language accepted by each of them is empty. So that's LP. So this actually it's undecidable. Okay, and I can show you why this is undecidable. Okay, so using proof by contradiction. So we assume there's a TM and okay decides LP. Okay, so when you say there's a TM and decides LP, okay, so that simply means if M is as a string, okay, is in LP, then N must accept M. If N accept M, that means M is in the language, or accepted by the tuning machine N. Okay, so N must be in there. Okay, since N is a TM, is a tuning machine, N is a tuning machine. Okay, and we can test it as an input. So this N is the tuning machine encoding for N. Okay, so basically N, uppercase N and lowercase n, that represent the same thing, but this N, lowercase n, are simply saying this is a binary string that represent N. Okay, uppercase N, the tuning machine. Okay, so we can test now this lowercase n. So there are two cases, but we only need to consider the first case. If N is in LP, okay, since you say N will determine LP, right? So if N is in LP, that simply say N must accept N. Okay, yes, tuning machine uppercase N must accept N lowercase n. So if N accepts N, that means N this lowercase n, this string is in L sub n. Okay, L sub n, and N is not empty because N, well, N is the uppercase N machine. You assume there exists this N, so N could not be empty. So using that, but the definition of LP simply say that LM, whatever M here, is empty. That means N, LN, now input is N, is the uppercase N is the tuning machine N, but L sub N is empty by definition. Okay, but you also say, oh, N is in LN. So N, if N is not empty but is in LN, so LN must be not empty, but by definition LN is empty. Therefore, that's a contradiction. So we show that the contradiction here, and simply because of the wrong summation, wrong assumption here, the TM, there exists a TMN. Okay, so N does not exist. Okay, if N does not exist, then the the assumption say the decidable N decides is impossible. So the LP is undecidable. But as a matter of fact, the LP is actually not RE at all. Okay, because since the N does not exist. Okay, uh, so LP is actually not RE. Okay, not just undecidable, but it's not RE. So that's all I have today for this video. I hope you enjoy. If you like, yeah, please like, share, okay, or you give a comment below. Thank you very much. Have a good day. Bye.